One of the more important limits in calculus is this trigonometric limit. What happens to this function, cosine of x minus 1 all over x, as x goes to 0. So recall with the limit we're talking about getting close to the point but officially not being able to land on it because we would be dividing by 0. And you can see that this function is very well behaved despite the fact that it's dividing by x, and it looks like kind of like a straight line there, and it very clearly goes through 0. So we're going to try to prove that limit, that the limit is cosine x minus 1 over x actually is 0. We're going to do this geometrically. So I've sketched part of a circle here with radius equals 1 and an angle carved out in this little pie shape, and that angle we'll call x. Because if we know we're dealing with a trig function, we need to talk about triangles, and particularly triangles of radius 1, because sine would be the height of this right triangle created by dropping a perpendicular here. So the height of that one is sine, and cosine is the length from the center all the way over to the corner, in other words the base of that right triangle we just created. In addition, because we're dealing with radians, the arc length between the edges of this pie shape here, the curved length along the outside, is actually the same as the angular measure x. That's the beauty of using radians. So our job is to look at this picture and see if we can figure out where the heck cosine x minus 1 might be located. When we're doing geometry like this, we're trying to associate a formula with the picture. So where on the picture would cosine x minus 1 be? And this takes a while. This is a creative exercise, and you might play around with it before you figure out that this little gap between the edge of this right triangle and the edge of the circle is what? The whole radius is 1. I've taken away cosine here, so the part that's left in that little gap must be 1 minus cosine x. Now officially I'm looking for cosine x minus 1, but you know what? I'll take 1 minus cosine x as a good starting place. So I've gone over that in red. So that's where my cosine minus 1 relationship is. What can I compare that to? The other part of the formula that I want is the part in the denominator. So here's the formula again. Cosine x minus 1, I found that guy, and I also need an x. Where's the x? Well, like the little joke, the meme joke says, there's the x right there. So now, x is this arc length, and that's important to me. And I've got this length of this triangle that's important. How do I relate those two things? Very often in this process of analysis we find something that's close to what we want if we can't get exactly what we want. The thing about triangles is we have lots of tools to deal with them. So if I think of this as the bottom of a triangle and then outline the rest of the right triangle, here's what I get. All I've done is outline the height of this right triangle, the vertical leg, and then I added a hypotenuse to it. So the leg that I'm interested in is this one down at the bottom, and I'm interested in comparing it to x. But you notice how close this hypotenuse is to x. X can't be much bigger than that hypotenuse. And this is part of the analysis game, finding something that's very good approximation to what you want in order to simplify it. And this is a simplification because I can figure out what that hypotenuse is and relate it back to this. I'm going to redraw my diagram now with just this part right here. So here's that little triangle blown up a little bit. We know the height's sine x, we know the base is 1 minus cosine, and whatever this hypotenuse h is, we know it's very slightly less than x, which was the arc length. I haven't drawn the arc length here. What do we know about right triangles? We know that the relationship between the two legs and the hypotenuse is given by the Pythagorean theorem. So that's going to combine this leg and get us in touch with x because it's very close to the hypotenuse. So we'll write down what the Pythagorean theorem says about this. So here it is. a squared plus b squared equals c squared, which we know is less than that arc length x squared. So this is the relationship I'm interested in. Well, 1 minus cosine x squared can be simplified by multiplying that out by itself. And when you do that, I'm going to write it all down. I skipped the gory details here, but you get sine squared, that's carried down. 1 squared is 1, cosine squared is cosine squared, and then we get negative 2 cosine x as the middle term out of that. But sine squared plus cosine squared is equal to 1 too. That's the Pythagorean theorem. And so this is really going to be 1 plus 1 minus 2 cosine x. This should give you a warm fuzzy feeling because you can see we're almost to our 1 minus cosine x over x if I rearrange this a little bit. At this point I need to think about the fact that when I take a limit, I'm going to be approaching from the left when x's are negative and from the right when x's are positive. And so I'd really like to be talking about the absolute size of these things. In other words, I'd rather have absolute values in here. So it's clear that the thing on the right is always positive. What about the thing on the left? 2 minus 2 cosine. Well, cosine can never get bigger than 1, so this is no smaller than 0. So I can put absolute value signs around both sides. So the 2's factored out. I've got absolute value of 1 minus cosine x less than, and I've split up x squared into absolute x times absolute x. Then I'm just going to rearrange a little bit. The reason I'm messing with these absolute value signs is because whenever you multiply or divide by a negative number, you have to flip the inequality, and I don't want to have to mess with that. So by making sure everything I'm dealing with is positive, then I can divide through by the x without worrying about flipping the inequality. And so I've divided through by 2, and we end up with this nice bound on 1 minus cosine x over x, which, because it's in absolute values, I can flip and make it cosine x minus 1. So I've graphed both the functions together. The red one is x over 2, and you can see that it's very close to 1 minus cosine x over x. And also, it's always on the other side of the x-axis from it. You see the straight line is always on top of it there, and it's always below it here, so it acts like an envelope. Because x over 2 goes to 0, it forces 1 minus cosine x over x to also go 0. Now I'd like to connect this limit to something we talked about before. It's actually in a previous video where I pointed out that sine x looks a lot like x when x is close to 0, and cosine x looks a lot like plain old 1 when x is close to 0. So we played this game where we pretended that cosine x was actually equal to 1, and we argued that 1 minus 1 is 0, and as x approaches 0, 0 over x is going to be 0, so that the limit would be 0. And then we checked that with the graph on Google. So that sort of approximation idea works sometimes, and sometimes if we push it too far it doesn't work. And I want to show you an example here of a subtlety involved with there. Suppose I change the x in the bottom to x squared. Now we've still got the top going to 0 and the bottom going to 0. But you might suspect that changing this from x to x squared makes the bottom go to 0 faster. Does that change the limit? If I make the changes to this approximation approach, I still got 1 minus 1 over x squared, so it looks like the limit would still be 0. Let's check the graph and see. Actually, we can see that it looks like the limit is negative 0.5. So that approximation approach didn't work. Let's take a more sophisticated look at it and see if we can figure out why it didn't work. The idea was that if I zoom in on cosine far enough at x equals 0, it starts to look like a flat line with height 1, y equals 1. See that? It starts to look more and more like a flat line. But if we zoom out, you can see that it's not really flat. It's got this slight curvature to it. and the difference between a straight line and that curvature must be what's causing the problem here. So we're going to see if we can understand what's going on with that. In the argument that we just made using the circle to find the limit, we found this really great approximation for it was actually 1 minus cosine x over x. We found that was very close to x over 2. So I'm going to use that fact here instead of the rather crude cosine is just 1. I'm going to replace cosine 1 minus cosine x over x with x over 2. So I've pulled out one of the 1 over x's, and then I'm going to remember that 1 minus cosine x over x is equal to x over 2, so I'm going to approximate this with minus x over 2 because I've got the sign reversed up there. This is a better approximation than the one where we just said cosine x is equal to 1. And you can see that in this case the x's are going to cancel out and we would get minus 1/2, which is what we observed on the graph. So this better approximation actually works. Well, here's the approximation, and what I want to do is solve that for cosine. So we'll just rearrange, we'll multiply both sides by x, and then we'll add 1. You see what we get is cosine x is approximately equal to 1, which was our old approximation, but now we've got this correction term that adds a little curvature to it, so it's 1 minus x squared over 2. Let's take a look on the graph at the difference between these two approximations. So here the blue line is our old friend cosine. The red line is the very crude approximation cosine equals 1 all along here. And then this orange or yellow line is the new approximation 1 minus x squared. We're really only interested in what happens near x equals 0, and all the action is going to happen right there. So I'm going to zoom in, and you can see that the new approximation, this gold line here, starts to match the curvature very quickly. And it's a very good approximation to the curvature of cosine up near the top. Whereas the first approximation, just 1, only really starts to get good now. Here you can see it starts to flatten out. At this point you can't even tell the difference between the second approximation and cosine. It's so good. So the reason that example, the last example with the x squared on the bottom, didn't work is because the approximation y equals 1 just wasn't good enough. And what calculus is going to let us do is have a whole toolbox to let us understand how to make better and better approximations, how those approximations help us understand the functions, sine, cosine, exponentials, and the whole basket of them that we're going to work with, how to construct the approximations, and how all this works together with limits.